And here's the example. All I did was I've given some numbers to the mass and to the spring constant, and then I've described how I push my particle initially. So I assume for this example that the particle or the object has a mass 2. I don't care about the units in this case. And I assume that the spring constant has a value of 8. And my assumption now is that at time 0, so at the start of the experiment, I'm pushing the particle to the left by 1 length unit. So x will be -1 when t is 0. And then I release the particle. The particle will start to move back to the equilibrium position. And I want to describe the motion of the particle. I can write this now as a differential equation, just like before. The mass is 2, so I get 2 times the second derivative of x. K is 8, plus 8 times x is equal to 0. That's exactly the equation we had. And now the information about the start of the experiment gives me what is called initial conditions. When t is 0, x has the value -1. And I want to release the particle, so I don't want to push it, I just want to let it go. It starts from rest, which means the velocity is 0. So dx dt, that's the velocity at time 0, is 0. So that's what I need to solve, right? A second order differential equation with 2 initial conditions that tell me where the particle is at time 0 and how fast it moves, namely not at all at time 0. Like I said, for this type of equation, there's a very nice method, and you probably know about this method, and you can do this a lot quicker, what I'm going to do now. I still want to talk you through all the single steps in this method, just as a matter of revision, if you want. The way to solve any differential equation is always the same. You first determine a general solution of your differential equation, and then you try to satisfy the initial conditions in the second step. How do we get a general solution of our second order differential equation? Well, for this type of linear second order ODEs with constant coefficients, we can always look for solutions in the following form. X of t is an exponential, e to the k times t. All we need to determine here is the number k, or the parameter k. And how do we do this? Well, we just substitute this form of the solution, or this form of the function, into our differential equation. Remember, our differential equation was 2 times the second derivative of x plus 8 times x is equal to 0. We already have x. All we need is to compute the second derivative. Well, we do this in steps. The first derivative, dx dt, just this differentiated gives you k times e to the kt. Second derivative gives you k squared e to the kt. And now I simply plug this into my differential equation, and I get this formula. 2k squared times e to the kt plus 8 e to the kt is equal to 0. Now e to the kt is an exponential function. I can simply divide through by this, and then I get an equation for k, which is called the auxiliary equation. And you see the coefficients in the auxiliary equations are exactly the same as in the differential equation, so you can simply write down this equation once you know how the method works. This is a quadratic equation for k. I will get 2 solutions, and they will give me 2 solutions x of t. Let's see how this works for the example. There's the equation again. Bring the 8 over to the other side, divide through by 2. So you see that k squared is -1 over 4, which means this quadratic equation has imaginary solutions. k12 is plus minus I over 2. Now I use these 2 values of k, and they give me 2 solutions, x1 of t, e to the I over 2 of t, and x2 of t, e to the minus I over 2 of t, or times t rather. And now I can use these 2 solutions to build my general solution of the differential equation. And here I'm actually using the fact that it is a linear differential equation. This only works if your differential equation is linear, but never mind, we can do this. What we do is we simply take a combination of x1 and x2, where we multiply x1 and x2 by numbers a and b. These are general numbers that we are free to choose. So the general solution of the differential equation is x of t is a times x1 plus b times x2. Now remember what x actually is. x is the displacement from the equilibrium position. So it's very much the position of the particle, which of course is something real, right? We're either to the left or to the right of the equilibrium position. So here, however, we have some complex numbers or imaginary numbers and some complex functions. So we want to make this look a bit nicer. And to do this, we need to use one of the major formulas in the analysis of complex numbers, which is known as Euler's formula. You probably remember this, at least you should. Euler's formula tells you that a number e to the I theta has real part cos theta and imaginary part sine theta. Okay, now remember what our solution looked like. There was e to the I over 2 times t and e to the minus I over 2 times t. So I can just use Euler's formula and apply it to x1 and x2. And then I get this line. Right? X of t is a combination of cosine and sine, which still has an imaginary part, of course. I can simplify this a little bit by observing that cos of minus tau, say, is cos of tau, so that's an even function, and sine is an odd function, so sine of minus tau is minus sine of tau. For the moment, I have nothing gained because I still have my I in there and it's still everything is complex. However, remember, I'm free to choose A and B. So now I simply introduce some new variables, which I call C and D, or new parameters rather. I set C as A plus B, and D as AI minus BI. And then you see all the terms cancel, and I end up with a very nice looking form for my function x of t, which is c times cos t over 2 plus d times sine over 2. The function x of t is the general solution of the differential equation. It contains two parameters, c and d. But remember, I still have two initial conditions that I can use. And in fact, I will use them to find the values of c and d. Now, before I do this, I want to discuss this general solution a little bit. So here it is again. What can we say about the function x of t? Well, if you look at what x of t is made up of, that's a cosine and a sine function. They are both periodic functions. And in fact, it's cos t over 2 and sine t over 2. So they are two periodic functions with the same period, which means the function x is a periodic function with the same period. And you can work out that the period of cos t over 2 and sine t over 2 is simply 4 times pi. What does this mean? Well, the particle starts to oscillate around the equilibrium position. And in fact, the period doesn't depend on c and d at all. It is the same for all initial conditions. The period of the oscillation only depends on the mass of the particle and on the spring constant, because this is really all we used to compute this general solution. So you can imagine that this makes an oscillation like this very well suited for measuring time, for example, because it doesn't matter where you start. It's a very robust process, and you can just let it go, and the particle will oscillate with the same period, with the same frequency, if you like. And so you can measure how often the particle oscillates, and this gives you a measure of time. Now, because this is a very simple type of motion, only made up of simple sine and cosine terms, we call this simple harmonic motion of the particle. That's a quite important term in mechanics. Okay, now let's just finish off the example, and let's compute the constant c and d. Remember, again, here's the general solution, and we want to now determine c and d such that the initial conditions are satisfied, which are x of 0 is minus 1, and the derivative at time 0 is 0. I can simply do this just by plugging in what I have. I compute x at 0, and I compute the derivative at 0. This is what I'm doing here. X at 0 is just c, because cos of 0 is 1, sine of 0 is 0. To compute the derivative, I need to differentiate, which is quite simple. You can do this yourselves. And you find that this is d over 2. And now I have two equations for c and d. I want that c is minus 1 and that d over 2 is 0. Therefore, the motion of p is given by x of t is minus cos t over 2. So this is the function that describes how the particle moves. And there we are. So what we did was we looked at a very simple model which describes the motion of a particle on a spring. In order to describe this motion, we need to find the position x of t at each time t. So we want to have a function x of t. To do this, we used Newton's second law and Hooke's law. And this gave us a differential equation which we used to determine a general solution first, and then for some initial data, we computed a particular solution. Now you could say that this is not a very realistic model, and you would be right. Because what we found was that the particle oscillates with a constant amplitude. And of course, in reality, what will happen is that the amplitude of the oscillations will get smaller and smaller, and at some point the oscillation will stop. Mainly for reasons like friction or air resistance and something like this. So if we want to have a more realistic model, we would have to incorporate other forces and other effects. And you can do this. This leads to extensions of the simple harmonic motion model, and these extensions are known as damped harmonic motion and forced harmonic motion. And you can look at your textbook to see how you can solve the equations for this model. And that's it.